Welcome back everyone to our Calculus 3 class notes. We're about a third of the way down on page 75 and we're in section 14.8 on Lagrange multipliers. So we just did an example that showed a substitution method where we didn't need Lagrange multipliers to be able to find the minimum value of a function subject to a constraint. So now we're going to talk about an example where substitution doesn't work and introduce Lagrange multipliers. So example 70, find the points on the hyperbolic cylinder x squared minus z squared minus 1 equals 0 that are closest to the origin. So it's clear from this graph that the answer should be the points 1, 0, 0 and minus 1, 0, 0. Those are closest to the origin of this hyperbolic cylinder. I typed the wrong thing because I had rotated the graph to see it better. Okay, so I'm going to try the substitution method and you'll see why it doesn't work in a bit, but I want you to understand why it doesn't work. So we want to minimize the square of the distance again. F of x, y, z equals x squared plus y squared plus z squared, right? Minimizing the square of the distance from the point on the hyperbolic cylinder to the origin. Subject to, the hyperbolic has to be on the hyperbolic cylinder, so x squared minus z squared minus 1 equals 0. So we're going to regard x and y as independent variables again. So z squared equals x squared minus 1. H of x and y is equal to f of x, y, and z now, where I'm going to let z squared equal x squared minus 1. So in other words, it's x squared plus y squared plus z squared, but z squared is x squared minus 1. So h of x and y is now 2x squared plus y squared minus 1. And when I look at the function h of x and y, its domain is the entire xy plane. I've made my substitution based on the constraint, so we should be able to solve it, we think. So partial of h with respect to x is 4x, set it equal to 0, I get x equals 0. Partial of h with respect to y is 2y, set it equal to 0, I get y equals 0. So it appears that the extreme value of h occurs at 0, 0. But wait a minute, I said it had to be on the hyperbolic cylinder. And there's no points on the cylinder where x and y are both 0, certainly not at the origin. So the problem is that we want the points on the cylinder where h is minimized. We want the points on the cylinder where h is minimized. The domain of xy, h of xy, is the entire xy plane, but we should not be including the band between x equals minus 1 and x equals 1. Right? We should not be including this band between x equals minus 1 and 1. So substitution doesn't work here. So I'm going to use Lagrange multipliers, and I'm not yet formally stating the method, but you'll see how it works by me walking through this example. So imagine a small sphere centered at the origin, expanding like a soap bubble until it just touches the hyperbolic cylinder. Now at each point of contact, the cylinder and sphere have the same tangent plane and normal line. So if the sphere and the cylinder are represented as level surfaces, so this is the cylinder of radius a, right? So x squared plus y squared plus z squared minus a squared equals 0. And g of x, y, z is the hyperbolic cylinder, x squared minus z squared minus 1 equals 0. Then if I think of them as level surfaces, the gradient of f and the gradient of g will be parallel where the surfaces touch, because remember these are orthogonal to the level surfaces, and the level surfaces just touch right there. So that means that if they're parallel, they're some scalar multiple of each other. So that means that the gradient of f is going to be equal to lambda, for some scalar lambda, times the gradient of g. So these lambda here are actually what we call the Lagrange multipliers. So I take the gradient of f, I get 2x, 2y, 2z. That's equal to lambda times the gradient of g, which is 2x, 0, minus 2z. So that gives us three equations. 2x equals 2 lambda x. 2y equals lambda times 0, so 2y equals 0, which does tell us that y equals 0. And 2z equals minus 2 lambda z. So for lambda equals 1, that means that I get 2z equals minus 2z. That's not possible unless z equals 0. Now if x is not equal to 0 on the cylinder over here, right, x can't be 0. So this means that 2x equals 2 lambda x. Lambda has to be 1. Okay, so for lambda equal 1, I know from this equation lambda has to be 1. For lambda equals 1, z has to be 0. So I got y and z 0. So the points we seek have coordinates x, 0, 0. So that means that x squared minus z squared equals 1 is the same as x squared equals 1, which means that x equals plus or minus 1. So the points on the cylinder, x squared minus z squared equals 1, closest to the origin are 1, 0, 0 and minus 1, 0, 0. I'll stop there and come back to this note in the next video.